Hi, everybody. So, today we're going to discuss the problem of chaotification. Okay, I'm going to give you some results from our recent paper, which was published in Nonlinear Dynamics, and the paper is called The Review of Chaotification Techniques for Discrete Time Systems. Okay, so in this work, we will only focus on discrete time. Okay, so chaotification, what is it? If you go on Google Scholar and search the term, you will find many papers on this topic. Well, the idea is this. As you already know, in the literature, there are many chaotic maps published. Okay, so let's say we have this initial, see the top line here, this initial chaotic map. Okay, this may be the logistic, the tent map, the sign map, the Chebyshev map, the Renouille map, whatever. Okay, the idea in chaotification is this. We design a new function, f capital, which can be composed with the initial seed map, okay, with the goal of creating a new family of maps, a generalized family of maps that is, in general, a more complex map compared to the seed. Okay, so the initial map is called the seed map, and the new map that we obtain is called the new family of maps. And we call this process chaotification because our goal is to create maps that have more complex behavior. So what do we say, what do we mean when we say more complex, right? Or more chaotic behavior? Well, this can mean a collection of different things. Well, first of all, with this new family of maps, one of the initial goals may be, for example, to achieve a higher Lyapunov exponent. So let's say, the logistic map has the highest Lyapunov exponent, I think is around 0.7. Okay, so by chaotification, we may want to achieve a new map that has a much higher Lyapunov exponent value. Okay, so this may be one goal of chaotification. Another goal would be to create a new family of maps that can achieve robust chaos. Let me remind everybody, robust chaos means that for a certain interval, for a specific parameter, we have no periodicity at all. So we have through and through chaos for all parameter values. Okay, so this is a very desirable property, especially in applications like chaotic encryption or chaotic security in general. Okay, so we may want to achieve this result. Okay, other results that we may want to achieve in codification, for example, may be to control the mapping domain, just like offset boosting, for example, in a specific family of maps, or maybe control the statistical properties of the time series, because as chaotic time series are, they have, statistical properties that are similar to random series, but they also have a lot of bias. So we may want to control this bias. Okay. And overall, we may want to achieve other stuff like having coexisting attractors or having hidden attractors. So the general goal of codification would be to define a new family of maps that has a richer dynamical behavior compared to the seed maps. Okay. But also, let me clarify, in codification, we are not aiming in designing one new map. Okay, we want a family of maps, and ideally, we want this family of maps to have these desirable properties that I mentioned for any seed function. So the seed in this chaotic family may be the logistic, the sign, whatever map, and in all cases, ideally at least, we want to obtain the same desirable results like robust chaos, hidden attractors, statistical properties that can be controlled, stuff like that. Okay, so this is the general goal of chaotification, obtaining more complex and more chaotic new maps. Okay, this is a very nice example of chaotification. It's from a recent paper in 2022. Now, the top figure is the bifurcation diagram of the sign map. You may be familiar with it. And you see that the original bifurcation diagram has some chaotic regions, which is a good thing, but it also has periodic regions. So you see from 0 to 0.7, we have period, then around 1.5, I'm sorry, around 2.5, around 3.5, we have some periodic regions as well. As you see right here, there are some small white gaps. Again, they signify that the map is periodic. So the original map has some chaotic regions, but also has a lot of periodic regions as well. After chaotification, the new map has a bifurcation diagram that you see below. And you see that it remains chaotic through and through, right, from 0 to 5. It has no white gaps, meaning that the map doesn't go through periodicity at all. Okay, so this is a case where chaotification leads to robust chaos, a very, very desirable result. Okay, so ideally in chaotification, we want to achieve stuff like that, more complex maps. Okay, now let's talk a little bit about this structure of chaotification. As you see, it's the composition of two functions, and the function is inside the small f, basically is taken from an existing seed map. And the seed maps that we usually use in the literature are the standard ones that you're already familiar with. The logistic map, the tent map, the sign map, the Renui map, the Sebisev map, which are all very well-known one-dimensional maps. But you may also see some two-dimensional maps like the Henon map, which is super well-known in the literature, okay? So most codification works in their examples use this collection of maps right here, okay? Now, the big problem, of course, these are already known. The big problem is designing the capital F, okay, the big function. And we did a very thorough review of the literature, focusing on the last 5 or 10 years. There are many, many different techniques, but most of the techniques follow some specific steps. Okay. So, for example, the most well-known technique is the use of the modulo operator. Okay. Modulo is very well known because it creates a lot of discontinuities inside the functions graph. Okay. So this is very desirable because it gives security, and also it's very useful in creating robust chaos. Okay. Moreover, modulo is bounded, so it can control the map's domain. Okay. So it's a very useful operation. I think most publications use the modulo operation. Okay. The second most popular technique is the use of trigonometric functions like sinusoidal or cosine. Okay, I have some examples here. Again, they are very valuable because they are bounded. And this means that if you use this function, the map is always going to remain bounded. Very desirable property. Now, of course, some of you may think, Lazarus, come on. Uh, Sine and trigonometric functions are periodic functions. How come a periodic function can be used to create chaos, which is unperiodic? Well, yes, it does. It's very useful. You will find a lot of papers on this result. So actually, periodic functions can create chaotic behavior. Okay, so these are the two most popular techniques. Other ones is the use of exponential functions. We saw a couple of papers do that. And also the use of piecewise functions, which can be either piecewise linear or piecewise nonlinear. Both of these cases are very popular in practice. And of course, there are a couple of other techniques that don't fit any of the above. For example, I have one here, which is basically sort of an internal feedback uh, technique that, again, gives very, very good results. Okay, so in the literature, there are many papers, and these are the most important techniques that they use. Okay. After obtaining the new families, most works have some simulations or have some numerical or mathematical results. Now, in most of these papers, we observe the fact that it is possible in most situations to generate robust chaotic behavior. As I told you, robust chaotic behavior is very desirable in practice and especially in applications related to encryption. So in many papers, robust chaos can be achieved. So this is very good. Now, a second observation that we have is that, unfortunately, not all works have mathematical results. Okay, so in many papers, but not in all of them, the authors also prove mathematically that you can achieve a higher Lyapunov exponent compared to the original chaotic map. Okay, so this is very, very important because we prove mathematically that we can have higher Lyapunov exponent. Okay, and this is the most basic result, but there are other mathematical results. For example, some of them study the existence of equilibria. So they have a lot of other similar theoretical results. Okay. Other than these two basic results, we saw that many papers achieve hidden attractors, which means that the maps don't have equilibria. Okay. Many maps also design a good bounded, I mean, they achieve boundedness on the chaotic map, and some of them achieve domain tuning, like offset boosting, for example. And also another result, which is of course very important for applications as well, is the fact that we managed to achieve an increase in the key space. Now, let me remind everybody, the key space refers to the number of parameters that the system has, okay? The initial conditions and any other control parameters that we are using, okay? So this is, key space refers to basically how big are the available options for choosing these parameters, okay? This is very desirable in applications like encryption and security because a higher key space gives us resistance to brute force attacks. Okay, so again, many papers focus on that, and we obtain very, very good key spaces indeed. Now, after reviewing many, many, many papers, okay, we have some additional observations from all these works. Okay, now let me tell you the basic observations. We saw that the modular and trigonometric operations are the most common, and indeed they are very efficient in achieving better chaos. Okay, when I say better chaos, you mean, you understand, I mean robust chaos, for example. Okay, but of course, modular and trigonometric are a bit computationally heavy. Okay. Also, specifically for the modulo operation, the REM function, we know that they can generate discontinuities in the map. And these discontinuities are very desirable because they can also create robust chaos, but also because we discard information through the modulo, they also give some additional security against parameter estimation attacks. So this is a very good result. Okay. Of course, trigonometric functions and modulo functions, and also piecewise functions, actually, they can help designing maps that are bounded. Okay, so they never diverge to chaos, I'm sorry, they never diverge to infinity. Okay, and we can also control the mapping domain for these maps. Okay. Moreover, some works, not all of them, focus on increasing the key space, which, as I told you, is very desirable for applications in security. Not all works care about that because obviously this is an optional application, but for us, we work a lot on chaotic encryption. This is a very important result as well. Okay, and then finally, most of the published papers accompany their theoretical results with some application to showcase the fact that the new maps are very useful in applications. Okay, uh, the most common ones are the ones that I already mentioned: encryption, then chaotic random bit or number generators, the well-known prbgs and prngs. Okay, these are the most common that we found in practice. And there are other applications, of course. For example, secure communications, which is another very common application. Here we try to use a public channel and transmit some sort of information using chaotic signals as sort of an artificial noise. Okay, a very interesting application. Compression, like text and image compression. Surveillance, like chaotic motion, chaotic patrolling in autonomous agents. And moreover, some works devote time to also perform hardware implementations. So like Arduino, microcontroller, FPGA implementations. These are also very, very useful because implementing chaotic systems requires a lot of design. And of course, it shows us that we can actually use chaotic systems in applications like security, in microcontrollers, in Internet of Things applications, and stuff like that. So these implementations are actually very important for the future of chaos. Now, as I told you, the field is very active. We found a lot of applications in the field. I believe within the next 5 and 10 years, there will be a lot more applications in codification and a lot more papers in codification. So I believe there are a lot of open problems. Okay, so although we achieve robust chaos in many papers, I believe there is a lot of room for improvement in designing new chaotic families that achieve robust chaos. Another very important topic of study is the design of hidden attractors through chaotification. Okay, a bit more theoretical. Of course, we need to keep in mind that ideally we want lightweight codification. We want computationally light techniques because ideally we're looking for applications of chaos. Okay, so we need to have techniques that are lightweight. And of course, a very, very, very big topic for the future is quantum chaos. Within the last 5 years, yes, there have been some works on quantum chaotic systems. Not a lot, but there have been a couple. I believe in the next 10 years, we're going to see a lot more papers published on quantum chaotic systems. So I believe quantum chaotification is going to be a very trending and very interesting topic to study in the future. Okay. We mostly focus on discrete time systems and quantum systems in the future, but of course the topic is open also for continuous time systems. There are published works there. But discrete systems are so lightweight, it's better to focus on them at the moment. Okay, so in the future, I believe we are going to see a lot more works published on chaotic discrete time chaotification and quantum chaotification. Okay, so as I told you in the description of the video, I'm going to put a link so you can download the article. If you have any problems or any questions, feel free to email me, of course, and I will be happy to discuss it, and I'll see you in future videos.